For this state of stress, we're going to find location of the principal plane, the principal stresses, and then the max shear stress and the corresponding normal stress. So I'm going to take it a little bit further than just finding those. We'll actually plot the rotated element to kind of see what it looks like. But first place to start is to go ahead and draw a Mohr circle for this. And if I look at the coordinates of the right side of the box, that should end up being a positive 50 in tension. The 40, because it makes the element spin counterclockwise, we're going to call that a negative 40. So normal stress, shear stress pointed up, positive pointed up. My point should be somewhere down here, 50, negative 40. The top and bottom of the box, that's a compressive normal stress. That's going to be a negative 10. 40 makes the element spin clockwise, so negative 10, positive 40, about right here. If I draw a straight line between those two, that would be the diameter of the circle. Center coordinate, of course, lies right here on the horizontal axis. If I spin this around, make a circle out of it, there's more circle. Principal stresses that I'm trying to find are all the way on the left and the right. This is sigma 1, the major principal stress. Back here is sigma 3, the minor principal stress. And it looks like from where I'm currently at, the I guess the best way to get there is to take my existing orientation, which is horizontal vertical sides, and then rotate counterclockwise in order to get to the principal planes. So the center of Mohr's circle is just the average of the two normal stress values, so that's 50 plus negative 10 divided by 2. So that gives me a center coordinate of 20. The radius, in order to find the radius, let's take a look at the triangle formed either on the right or the left hand side. I'll look at the one on the right hand side. So if I take the coordinate 50, negative 40, I project a vertical line up, then I have a little triangle. It's going to look something like this. Okay. This counterclockwise angle is 2 theta p to the principal planes. The vertical leg is just the y coordinate. I'll just look at magnitude, so I don't really need to worry about the negative 40. I'll just put 40. The horizontal leg is going to be the difference in the two x coordinates, so that's 50 minus the center coordinate of 20, which gives me 30. So in terms of the radius, looks like this is actually a 3, 4, 5 triangle, so 30, 40, 50. So the radius is 50. As far as the orientation of the principal planes, 2 theta p is the inverse tangent of 40 over 30. So 2 theta p ends up being 53.13 degrees, and theta p, half of that, about 26.6 degrees. Okay, so that is the orientation of the principal planes. That's one of the questions they're asking. Next is what are the principal stresses? So we have sigma 1 is the center plus a radius. So that's going to be a center of 20 plus a radius of 50 gives me 70 megapascals. Sigma 3 is the difference, 20 minus 50, negative 30 megapascals. So those are the principal stresses. And if I wanted to draw that on an element, rotated element, first I have to remember that the element is going to rotate, looks like counterclockwise, 26.6. So if I rotate it counterclockwise, something like that, this angle, theta p, 26.6 degrees. The principal stresses, let me see, the right side of the element, which was the 50, negative 40 coordinate down here, ends up rotating counterclockwise and goes to sigma 1. So that means that vertical face rotates counterclockwise, ends up here as sigma 1. And sigma 1 is a tensile stress. I'm going to put the arrowhead right there. Call it 70 megapascals. Of course, I have 70 megapascals on the other side. No shear stress whatsoever. When I look at the normal stress and shear stress on the top of the element, that was the coordinate negative 10, positive 40 up top. When that rotates counterclockwise, it transforms into sigma 3. So top of the box, or top of the element, rotates counterclockwise, it ends up here. And that ends up as a compressive stress of negative 30, so arrow pointed towards the element. Of course, it's the same on the other side. 30 megapascals shown in compression. So that's what the state of stress looks like on the principal plane, and those are the principal stresses. So for the max shearing stress, or max in-plane shear stress, and the corresponding normal stress, it looks like on Mohr's circle, oops, instead of going to the left and right side, now I need to go up to the top and bottom of the circle. So I'm looking at this vertical diameter. From the black line where my current state of stress is, instead of rotating forget it. Instead of rotating counterclockwise, now it looks like I need to rotate clockwise. And I'll call that 2 theta. So 2 theta would be, just from the geometry there, on looking at the circle, it's going to be 90 degrees minus 2 theta p. Or theta is just 45 degrees minus 26.6, which gives us 18.4. Okay, so the shear stress, the max in-plane shear stress, is just simply the radius of the circle, which we've already calculated as 50 megapascals. And the normal stress that accompanies that max in-plane shear stress, that's just the coordinate of the center of the circle. That was 20 megapascals. So if I want to, let me see, so that's the answer, I guess, 50, 20. If I want to look at the rotated element like we did with the principal stresses, then instead of rotating the element counterclockwise, I'm going to rotate it clockwise. something like that. And when I rotate it clockwise, 18.4 degrees, then the shear stress ends up going to 50 megapascals. In order to determine the direction the shear stress is pointed on these different faces, let's look at the right side of the box, or the right side of the element here. That was the 50, -40 coordinate over here on the circle, and that rotates clockwise down to the bottom, and down at the bottom that would be a -50. So again, right side rotates clockwise, ends up here, and on that face I would have a -50. So what a -50 would do would spin the element counterclockwise. Of course, on the other side it's the exact opposite. You can step through the reasoning here to find out what happens on the top and bottom of the element, but of course you're going to get complementary shear stresses, so you're going to get the head-to-head, tail-to-tail on the other side, and it should be 50. For the normal stress, again, the center of the circle shows you that you're not getting rid of your normal stresses. You're stuck with a normal stress of 20 megapascals. It is positive, which means it's tension. So on every face, you get 20 megapascals. Okay, and that's what the state of stress looks like. Notice from the principal plane, which was this first element that we plotted, to the max in-plane shear stress, is 45 degrees apart. That's always going to be the case. Principal planes are going to be 45 degrees away from where you get your max in-plane shear stress, just like in Mohr's circle. I guess it's a little more obvious where your principal stresses are. Sigma 1 and sigma 3 on the horizontal axis is going to be 90 degrees, right? 2 theta, twice as much, 90 degrees from the top and the bottom of the circle.